So now let's see some more examples of clustering algorithms. We are going to start by looking at a problem with prototype-based clustering. So basically two problems, which is the choice of the number of prototypes and also how we can use the prototypes to assign the points to clusters. We are going to see affinity propagation clustering that solves one of these problems. The number of prototypes is not something we need to determine in the beginning. And then we're going to see density-based clustering, which does not need prototypes, so uses a different method for clustering. And we're going to see a bit about how to validate different clusters. So when we do prototype-based clustering, like k-means, we are basically doing two things. We are selecting a few prototypes to represent the cluster, and we are assigning the points to the closest prototype. So basically, in general, we are not looking at what the other points are doing. We are just saying that this point belongs to this cluster because of the distance to the prototype. So we only look at the point and the prototype to determine if the point belongs to the cluster. Now, this is good for globular clusters if they are well separated, and if we choose the right number of prototypes. So in the case of k-means, since we need to choose the prototype in the beginning, the number of centroids we're going to use, this can be a problem because if we miss the correct number, we can have incorrect clustering like this. So this works fine if we choose 3 clusters, which is the number of clusters we have here. It doesn't work so well if we choose the wrong number of clusters. It's also not very good for clusters that are not globular, because since we are assigning each point to the closest centroid to determine which cluster it belongs to, this clustering algorithm ignores the fact that these belong to 2 different clouds and puts them together and so forth. So we are only looking at the relation between each point and the centroid of the cluster, and so we are ignoring the information on the pattern for our data. It's also a problem when we have different sized clusters or different variants in different clusters. Because since we are looking at each point and assigning it to the closest centroid, if we have a very small cluster here, a tight cluster, and a very spread out cluster here, some points that would intuitively belong to this larger cluster are actually placed in the smaller one because they are closer to that centroid. So we have several problems here in the way we are assigning the points to the centroids, and also in the choice of the number of centroids in the case of k-means. Of course, this may be a problem in cases like this, but it's actually an advantage in cases like this, where we actually want to partition our data into a fixed set of clusters in order to do, for example, vector quantization. So it's not necessarily a defect in all cases. In some cases, it's not a bug, it's a feature. So it depends on what we're trying to do with the data. So for k-means, we are choosing first the number of clusters, then we partition everything according to the closest centroids to assign to each cluster. This is useful in some cases for vector quantization, for example. In other cases, we must take into consideration these features of k-means clustering and decide whether or not it's appropriate. So if we want to separate clusters that have very different sizes, k-means will not work very well in this way. Also depends on the shape of the clusters and so on. So another prototype-based algorithm that solves that problem of deciding the number of clusters, although we can influence the number of clusters indirectly, but this is affinity propagation. And the basic idea here is we can imagine that all the points are casting votes for candidate points that would serve as representatives of a cluster. And each candidate is also looking at the votes it's receiving and giving some feedback on how appropriate it would be for that point to represent the other. So we can see this metaphorically as letting the points vote among each other about who is going to be the representative. So for this, we need only a similarity matrix between all the points. Note that for k-mean, we also have this additional requirement in that we need to be able to compute the position of the centroids. So if we are unable to compute a midpoint between points in our data, we cannot use k-means. This can happen, for example, if you're comparing text documents. You can measure distances or similarities between text documents, but it's very hard to compute the midpoint of a set of text documents, because that doesn't make much sense. What would be the middle point? So there is a variant of k-means that can work with that, k-medoid, that chooses points as centroids, so it doesn't compute the mean point, but chooses one that is closest to being equidistant from the others, so to speak. Affinity propagation is something like that. You don't need to compute averages of sets of points. You are only using the points as representatives of groups of points. But we need a similarity matrix, which is a way of measuring which one is closer to each other, to another, and we use the diagonal of the matrix, so the self-similarity of the points, to indicate a propensity for points to be a prototype. With this parameter, we can, by changing this value, we can end up having more clusters or fewer clusters. However, we are not determining exactly how many clusters we have, so we can let the data determine that. And then we have these two matrices, which are the responsibility that one point I sends to point K to basically tell the other point that it can be a good representative for point I. And we have the availability also from I to K, but this is basically what the candidate K can say about how suitable it is for that point to represent the other. So what we start with responsibility and availability at 0, and now we have these update rules. I'm not going to go into much detail, but the idea here for this responsibility matrix, the R matrix, we are going to look at the similarities between points. So each point I is going to look at similarities to all the other points and subtract the maximum similarity of those points to others. So basically, it's going to look for a good representative in some points that is similar to itself, and ideally dissimilar from the others, or has a small similarity to all the other points. So basically, at first, this availability and similarity and responsibility are at 0, so we start by just using the similarities, but as we start updating, we are checking both the responsibility each point assigns to candidates that will represent them, and also the availability of the other candidates to represent the point. So this also starts affecting the computation, the update of the responsibility here. And for the availability, we are looking at the self-responsibility of the point. So this is basically how that point feels able to represent not only itself but also all the others. So this self-responsibility indicates the propensity at that moment for that point to be a prototype. And we are going to look also at the responsibility this point is assigning to others. So basically, this will determine we can imagine this as being looking at the same problem from two sides. In one case, the points are trying to choose which is the best prototype for each of them, and on the other case, each point is looking at the votes it's getting and trying to determine if it's a good prototype for all those that are casting their votes on them. And now we can look at this self-availability as evidence that K is a prototype. So basically, we are going to look at the maximum of the availability and the responsibility for each point. we look at the responsibility it's assigning to the other points and how other points are feeling available to represent this point. And if we find that the maximum is the point itself, then this point is a prototype, is a representative of a group of points. If we find that the maximum is another point, then this point is casting its vote on another to represent. So how does this work graphically? In the beginning, we don't have many representatives, so each point is basically alone, representing itself. The large circles here are the prototypes that represent clusters, and the small dots are those that have cast a vote on one representative. So we start with basically these ones that are more isolated have chosen their representative, but in the beginning we mostly have one cluster for each point. But then, as the iterations go, we start converging into points that are good representatives of their neighbors. This is not monotonic, so we can have at some point it can have fewer clusters, and then as we continue, the clusters can break down and separate, but eventually it will converge, and the number of clusters will be determined in part by the self-similarity that we feel in the matrix in the beginning, but also mostly by the way the data is, or the shape of the point in the data. So we are not determining in the beginning how many clusters we are using, we just let the points decide. However, note that we also have this problem with prototype-based clustering, in that we are looking at pairwise distances here, and we are considering whether one point will vote on that representative or the representative accepts that point, and so we can end up with effects like this. For example, here is one cluster, here is another cluster, and this would not be a good way of clustering these data. So we don't need to decide how many clusters we are forcing the algorithm to produce at the end, although we can affect that with those parameters, but once the clustering is done, we have no guarantees that it will follow some kind of contiguity or density and so on, because it's still a prototype-based clustering and it's looking for distances to the prototype. So this affinity propagation you can use here with the affinity propagation class in scikit-learn, and it solves part of the problem we had with k-means in prototype clustering, which was the need to determine the number of clustering, but it still is not good for some cases like this, where clustering would have to be determined by something other than just the distance to a prototype. So let's see an example of an algorithm that can solve that. This is density-based spatial clustering with noise, dbScan, and the basic idea here is that we have these two definitions, the neighborhood epsilon of a point, which is the set of points that are below this epsilon distance to that point, and this mean point, which is the minimum number of points in that neighborhood for one point to be a core point. So if a point is surrounded by a neighborhood with more, or with at least that minimum number of points, it's a core point. If it's not, then it's not a core point. So now the algorithm is simple. It's based on this notion whether we can reach from one point to the other by going through points that are in the same neighborhood of one another. So basically we are looking at the dense region and trying to merge together all the points that belong to the same dense region. And the algorithm is simple. For each point, we are going to count the number of points in the epsilon neighborhood. So how many points there are within that epsilon distance. If this is less than the minimum, sorry? Yes, the epsilon and the minimum number of points are two parameters that we have to give. So if this is smaller than the minimum number of points, then we presume that this point is noise. So if there are not enough neighbors in that neighborhood, we presume that the point is noise, it's not in a dense region. Otherwise, if the neighborhood is at least this number of points, then the point P is a core point, and it belongs to a cluster. So we create a cluster for that point, and we put there all the points in the neighborhood. So if there is a core point, then all the points in the neighborhood will belong to that cluster. If any point in the neighborhood already has a cluster, so it was already a core point that we had identified previously, we merge the two clusters together. So the end result, after we look through all the points, is something like this. Points here are not are noise, so they don't have the right number of neighbors, and they are not neighbors of any core point, so they don't belong to any cluster. These points represented in black. These points here belong to one cluster, and these to the other, because of the contiguity of core points here. So every time there is a core point in the neighborhood of another core point, the clusters are merged.
How do we merge them together, two clusters together?
If one point is a core point, so it has at least a minimum number of points in the neighborhood, and if one of the neighbors is a core point, so if there is one core point there, the two get merged together. Yeah, they would. If it has this minimum number of points, then it's a candidate cluster. But if one of the points already belongs to a cluster, then they are merged. So you can imagine that this is what happens here. You have, say, one point here is a core point because it has a minimum of those minimum points in the neighborhood. When you figure out that this one is also a core point, then the two clusters are merged together because they are in the same neighborhood. And as you do that, the cluster will grow and spread over here, and so this becomes a single cluster because it's a contiguous dense region. If this continued here, for example, then we would have a single cluster because all the core points would be then reachable in that case. Okay? These points outside, they have no neighbors that are core points, so they end up being noise at the end. So these don't have an assignment to any cluster. You can use dbScan here with this class. So you can specify the epsilon value, that distance for the neighborhood, the minimum number of points, it's called mean samples in this case, and you can also use different metrics for the distance, but the default is Euclidean, it's the one we usually use. Okay, so now we saw some examples of clustering algorithms. We'll continue with other examples next week, but now we're going to look a bit into how we can validate clusters. So what kind of metrics we can use to validate clusters. In supervised learning, this is pretty straightforward because all we need to do is define a measure of the error between what we're trying to predict and the actual value. So our predictions and the actual value that we're trying to predict. For clustering, it's a lot harder to determine what counts as good clusters because here we don't have a clear objective of trying to predict something. We are trying to transform the data in some way that is useful, for example, to help us understand the data. So the definition of a good cluster becomes a lot more vague and a lot more variable depending on the actual application. So we need to consider different contexts, like determining whether or not there is some inherent structure in the data, or if it's just a set of points in some cloud, determine how many clusters we should use to group the points together, evaluate how well the clusters we generate fit some assumptions or some structure we know independently from the data. And this can be either with or without external information, so we can actually have we can apply clustering either in the cases where we have labels and we can compare the clusters with the labels that we know, or we can compare different sets of clusters. So we clustered our data in one way and now we're clustering in a different way, and we want to have a measure of how similar those clusterings are. So there are different contexts in which we may need to evaluate clustering, and exactly what we use, what we measure to do this evaluation will depend on the context. So let's focus now on what we can do without referring to any external information. So we are only using internal indices, internal indicators of how good our clusters are. And we can consider, I'm going to show 4 different measures. So basically, cluster cohesion, we are seeing if our clusters are tight, are well grouped together, so not very spread out. Cluster separation, we can measure if the clusters, different points in different clusters are sufficiently distant from one another. And then we have some more specific measures. For example, if we want to use prototype clustering, then it's easy to just compute the distances to the prototypes and have a kind of this sum of squares error for those clusters. And also we can combine these in the silhouette score. We have a combination of these measures to try to evaluate clusters. So if we have some similarity measure, then the cohesion of a cluster can be the sum of the similarities of all pairs of points within the cluster. Note that if we have a distance measure, then the distance will actually tell us the spread and not the cohesion of the cluster. So remember that depending on what we are measuring, if we are measuring similarity, then a high value means that they are close together. If we are measuring distance, it will be the other way around. For the separation between the clusters, we can check the similarity between different points in different clusters, or if they are prototype based, we can just check the cohesion by measuring the similarity between a point and the prototype, the center of the cluster, and the separation by the similarity between the centers of the cluster. So this is the basic idea. We want to check. Yeah. Now this is a similarity. So this is a more general. Distance has a very precise mathematical definition, but a similarity is just a way of measuring how alike they are. So this is something often the measures that you can use to compare things do not actually work as distances. For example, the distance between a knife and a fork is not something we can maybe assign a similarity and say that some of them are more similar or more different, but it's hard to project that in a way that is actually works as a distance mathematically. As long as we have values to measure, we can do that as a similarity. It's a broader notion. If we have distances, then we can actually do this kind of sum of squares error by, for example, summing the distances to the centroids, or compute the distances between the points, and so forth. One useful measure is this silhouette score, where we can compute the average distance of points within the same cluster, and the average distance of any point to a point inside the nearest cluster, so the one with the smallest average distance. And this, the relation between the two gives us both the idea of the cohesion of the clusters and their separation after the clustering is done. So the silhouette score is the difference between the two, so the average distance of any point to any point in the nearest cluster, but not in the same cluster, minus the average distance of any point to any point in the same cluster. And this is divided by the maximum of the two. So if we have a very large distance to the nearest cluster and a very small distance within the cluster, the silhouette score will tend to 1. This would be the highest value possible, where this one is 0, and so we divide by the maximum and we have 1. So the highest value for the silhouette score would be 1 at the limit where the clusters are infinitely compact or infinitely away from each other. On the other side, we can have clusters that are so mixed together that the average distance within the cluster is actually larger than the distance to the nearest cluster. So they could be completely overlapping, and we get a very small distance to the nearest cluster compared to the distance within the cluster, and then this becomes negative, so the lowest value would be -1. And between these two values, we have an idea of how compact and spread apart our clusters are. So this works well for some kinds of cluster. To do this, you only need to use the silhouette score, and you give the data points, so the coordinates for the data. Remember that here you actually need the distance to compute the silhouette score, so you give the coordinates and the labels for the clusters, and this function computes it automatically. And this works well for compact clusters that are relatively spread apart. So, for example, if we hit on the right number of clusters, in this case, we have a high silhouette score. If we don't have the right number of clusters, for example, we use 2 clusters in this case, then the silhouette score drops, and we see that we don't have as good a clustering as we had before. It's not that good when the clusters are not that compact. So, and in some cases we can have a low silhouette score if the clustering is wrong, but sometimes we can have a low silhouette score even when the clustering is right. For example, in this case, we have a very low silhouette score for this one, even though the clusters seem to be okay. This is because distances within the cluster are actually large compared to also to distances between the 2 clusters. So we can have a low silhouette score in some cases, even though clustering is good, if our clusters are not compact and well separated. So this would be another example for also note, for example, here we have a silhouette score of 0.628 in this case, so this is not a good clustering for this data. Here we have a silhouette score that is very close to that one, even though this seems to be a better clustering. The reason is that these clusters are now too close together, not well separated, and this lowers the silhouette score too. So basically, silhouette score is not a magical answer to everything, but it gives you an idea of how cohesive and how separated the clusters are. So if that is the kind of clusters that you expect, it's a good measure to try to optimize parameters like the K and K-means or something like that. If the clusters do not have that shape, then it's probably not a useful measure for this kind of cluster. We can also have, so we saw here examples of internal indexes where we are only looking at the clusters. We can also use external indexes. If we have information about ways of grouping the data, we can compare our cluster to those other labels that we can have. This can be an external index, something like classes if we are dealing with data like we used in supervised learning, so we already have the class labels, and we can try to see if our clusters match the class labels. Or it can be a relative index if we are comparing with some different clustering algorithms. So it's not so much in the data, but we already clustered in some other way. We're going to see a bit more about these external indexes next week, because your assignment will also have these available. But basically the message I like to end with here is that this is actually a very difficult problem, because note that the difficulty starts right at the beginning when we want to define what clusters we want. So it's always an open question how we want to group things together. So the algorithms and then the validation of the clusters are all dependent on that, and it's mostly dependent on the choice that we do for how we want to define the clusters. So you have to consider lots of different possibilities and to check if the measures you are using are adequate for the kind of clustering that you want and the kind of algorithms that you're using. Okay. So to sum up this part today, we saw prototype-based clustering. K-means is an example of a prototype-based clustering method where you specify the K, and this can help you partition your data into a fixed number or predetermined number of clusters. With affinity propagation, we don't specify directly, although we can influence the number of clusters, but we don't specify them directly. and the number of clusters emerge more naturally from the data. However, with prototype-based clustering, we are always looking at the distance between points and the prototypes, and this mostly ignores the general shape of the data. Density-based clustering does things differently, like we did in DBScan, and it will group points together depending not only on their distance to some prototype, because it doesn't use prototypes, but depending on how all the points are close to one another and the overall shape of the distribution of data. So for some things, this can be much more useful for representing the shape of the data. But note that there are some applications like vector quantization where k-means, for example, is better. And then we saw basically the problem, not so much the answer, but the problem of how to validate clusters. We are not going to go into much detail here, but this will be one important part of your second assignment. So basically, you'll have a problem where you have to think about how to do this, how to solve this validation problem, try to assess your clustering. So you have these two papers for the Affinity Propagation and DBScan. This one is especially important, DBScan, because it will be part of your assignment, so you'll have to read that paper for your assignment and use the method described there to adjust the epsilon parameter. And also you have scikit-learn has lots of documentation and demos on different clustering algorithms, so you can take a look at that too.